Hi folks, this is Gordon Parker from Michigan Tech, and in this video we're going to do a little motor modeling. Now, I've been wanting to do this video for quite a while now, and it's going to be a little bit on the long side, but hopefully it has a little bit for everyone. The first thing we're going to do is look at some pictures of what's inside a motor, but then we're going to go ahead and strip one down and then also look at the inside of a gearbox, a planetary gearbox. That's pretty fun. Then we'll go back and do some modeling, do an example, and then some Simulink Simscape. So before we get started, let's look at some motivation and goals. Control systems often have some sort of actuation, and DC motors are a real common form of actuation, so it's good to look at those. One of the interesting aspects of control design is that you often have to specify the requirements for the actuation, and to do that you likely will need to design the controller, and the actuation may present some additional dynamics into the closed loop system. So there's this circular sort of thing going on. And the example that we look at is going to have a motor that has dynamics, of course, that ties into the dynamics of the system that it is actuating. That sounds a little bit awkward now, but when you see it, I think it'll make sense. By the time we're done with this, you should be able to identify the main parts of a DC motor and the gearbox. Then you'll also be able to use the motor equations, there's a couple that we're going to look at, to generate differential equations of dynamic systems that are actuated by motors. So here we go. We can see here a cutaway of a load, a gearbox, and a motor. And let's go ahead and work right to left first, sort of at the high level, and then we'll work left to right a little bit lower level. So what we have here is a load, and it's in some sort of a support, and notice all these bearings that are floating around. Well, they're not floating around, but there's a lot of them in here, and they're very important. Specifically, if you're going to attach some sort of a load to, in this case, a gearbox, you want to make sure that you support that load nicely, and that's why I showed these bearings. Okay, so here we have this load, and it's attached to a gearbox, which is sitting here via a flexible coupler. Now, a flexible coupler in this context isn't flexible in torsion, it's flexible in the vertical plane that we're looking at here. And the reason for that is so that you can have a little bit of misalignment between this and this. Okay, so that takes us on to the gearbox. It's a planetary gearbox. We'll look at some details of that in a second, and here is the motor. Now the gray that you see, in this area is the outer part of the motor. The stuff inside that's in green and gray right here are what I like to call the rotating bits. And we'll have a look at that when we tear down a motor in just a minute. Now let's move through this left to right and go into it in a little bit more detail. So let's start with this. It's the armature, and it is part of the rotating bits. It's attached to this commutator, and the commutator is attached, in a sense, via brushes to the wires that are the things that are attached to the power supply that make the motor spin. Now, after we tear down the motor and we go back to the notes, we'll talk a little bit more about how the interaction of the magnet and the armature arises and generates a torque that actually spins the armature. That takes us to here, which is the business end of the motor. It's the output shaft of the motor. Oh, notice back here we have a little tiny shaft sticking out the back end, and that is useful for attaching encoders or other types of sensors. An encoder just measures the angle of the armature. Now this business end of the motor is attached to the planetary gearhead, which is here. Specifically, it's attached to the sun gear, and around the sun gear are some little planets. Now I've only shown 2 here, but in the motor that we tear down, you'll see 4. And if you look real close, you can see these little tiny pins, which just means that those gears are attached to the carrier, which is kind of the business end of the gearbox. And that's what is attached via the flexible coupler to the load. So now that we've seen a pictorial view of the inside of a motor and gearbox, let's look at a real one. Right, so here we have two DC brush motors, and we're going to tear into them a little bit to figure out how they work, or at least see some of their components. This one we're going to use to have a look at its permanent magnets and also its armature so that we can start getting a sense of the mass associated with that armature. It's not necessarily a trivial thing. This one we're going to crack into the gear head. So with that, why don't we go after this one first? And you can see I've already done some of the heavy lifting in terms of taking it apart. Now, let's have a look at it. Here's the business end of the motor. It has a pulley on it for a belt. That's great. The back end has the armature shaft sticking out the back so that you could put an encoder back here if you wanted to. Beautiful. Nice little motor. This is where a brush would be. The brushes are long gone. And here's the other one. So there would normally be leads coming out here, and that's where you would put the power supply to get it to spin. So let's take it apart. Look at how easy that is. Oh my gosh. Now, I'm going to pop this off. So there we have some housing for the back. Here's a little bearing on the back end. It's all good. And these are the magnets. Pretty cool. The way they've designed this, that they actually have the magnets on the exterior of the motor. And you can see they're quite magnetic. Let's keep pulling some of those off just for fun. Look at all those magnets. Probably need to get those a little bit out of the way so they don't go sticking to things. Now let's take the body off, and here we have the armature. Now I have a little bit of the housing still attached, but it's aluminum, pretty lightweight, but the armature is significant. It's probably about a half a kilogram. And the diameter of this armature is about 3 centimeters or so. So if you were to calculate the mass moment of inertia of the armature, you would take a half times its mass, which is another half a kilogram, times r squared, 0.015 meters squared. So you get about 50 times 10 to the negative 6 kilogram meter squared. Sounds like a small number, but that's actually, fairly significant. So there you have it, the inside of a motor. Now, if I was to pop this off, we would see another bearing right here. And that's about it. Beautiful thing. Now, I'm not going to reassemble that. That would probably go horribly wrong, so I'll just move this out of the way. And now we'll take a look at that gear head. Ta-da! Okay, so we have a smaller motor here and a gear head. This is a Planetary gear head. It's about a 3-to-1 gear ratio, and we are going to tear into it a little bit. So the first thing I'll do is just get the gear head off the motor, and then we will take the gear head apart just a little bit. There we go. Have to give it a little firm tug. This gear head's kind of cool, actually. It's got an encoder built into it. So this encoder is measuring the shaft rotation, the output shaft, which is right here, of course. Almost got it. Oh, I think I got it. There we go. We can say bye-bye to the motor. It's got this little adapter on the output shaft of the motor, which is fixed onto it by a little set screw. And it has a little, spline type arrangement where that, I'll put this over here, sticks into the output side of, the input side to the gear head, which you can see right there. And it is liberally greased with a bunch of lithium grease. That's the white that you see in there. And let's get this off. I know my hand is blocking the action, but that's okay. There we go. Now, I'll just leave this attached for now. And what I'm going to do is rotate the output shaft of the motor one time, and you can see that input side to the gear head. Oh, I said output shaft of the motor. I meant output shaft of the gearbox. So I'm rotating the output shaft of the gearbox, and I'll do it one time starting now. And if you watch that inner piece, that's about one rotation. That inner piece rotated 3 times. So that means that the motor would spin 3 times and the output shaft once, hence a gear ratio of 3:1. Well, let's take this off, and now we can see the wonder of the Planetary gearhead. Look at that beautiful thing. So I'll rotate this, hold that constant. Is that far out or what? So now we can identify this as being the sun. It has 4 little planet gears around it, and this outer one is the ring gear, which is stationary in this case. So the gear ratio of this could be calculated as the number of teeth of the ring divided by the number of teeth in the sun plus 1, and that'll give us the gear ratio. So this would be, I don't know what it is, like 70, let's say, teeth here, maybe 35 on the sun. Divide those two, you get 2 plus 1 is 3. And that is about it. So we've taken a look at an armature. It's got some mass, saw some kind of cool magnets, and now we've taken a look at a Planetary gearhead. It's a beautiful thing. Okay, so back to the boring slides. Here's some notation, and I'm not going to go through this in complete detail. We'll be using some of this notation throughout the rest of the slides. But I do want to point your attention to a mistake that I noticed here, that I had the units on the back EMF constant upside down, so it should be volts per radian per second. And we'll see how that factors into things just in a minute. To help us make sense of the modeling of a motor and a gearbox, it might be helpful to go back and have a look at the video on gears. And that's where I introduced this notion of effective inertia that was J1n squared plus J2. And in that video, I used the small gear radius, or the small gear, as gear 1, and the larger gear as gear 2. The way that maps to the gearbox for the motor is that theta 1 becomes theta m, and theta 2 becomes theta gear. And I can see here in the notes that I have a little mistake. I have the n squared theta m and n squared theta m dot, and that should be n squared theta g and n squared theta g dot. But the idea here is that if you have a moment acting on the motor's armature, let's say a damping moment, that would look like a bm times theta m dot, then it presents itself on the output of the gear as multiplied by n squared. So the bm theta m dot would become, for instance, a bm n squared theta g dot. And we also had in the gear video the notion that the output torque of the gear train tau 2 is equal to n times tau 1. So just to formalize this a little bit, we have the effective inertia is equal to Jm n squared plus Jg, where Jm is the mass moment of inertia of the armature, and Jg is the mass moment of inertia of the gearbox output side. So it includes everything that's inside the gearbox and any sort of relationships that amplify little internal inertias and so forth, but the bottom line output inertia of that gearbox we're going to define as Jg. So the effective inertia of the gearbox and armature is this JEF. The other important point is that the torque on the output side of the gearbox is equal to eta n tau m. Let me explain those terms. Eta is the gearbox efficiency, and that's the first time that we've really looked at any sort of efficiencies related to gears and gearboxes, but that's the efficiency of the gearbox. N is the gear ratio, and tau m is the torque that's applied to the armature of the motor due to the interaction of the armature windings and the permanent magnets inside the motor. Now here's the two main motor equations. That torque that's applied to the armature due to the electromagnetic coupling of the magnet and the armature winding that has a current through it, so it's producing its own magnetic field, is tau m, and that's equal to kTIA, where kt is some torque constant associated with the motor, and Ia is the current that's running through a particular winding of the armature. The other motor equation is the back EMF equation. So here we have it in 4, where we have E, which is a voltage, is equal to Ke, another constant associated with the motor, times theta m dot, the spin rate of the armature itself inside that motor. Now what's interesting is that if you use rational units for Kt and Ke, consistent rational units, then the physical value, the numeric value of Kt and Ke are exactly the same. Modeling a dynamic system with a motor is basically using these equations, 3 and 4, and the notion of the effective inertia in 2, and perhaps also this little torque equation, along with a circuit and a free body diagram. And then you're off to the races. So let's first just generate the equations of a motor without it being attached to any sort of other dynamic system. And our starting point is going to be a little circuit. Now this circuit represents physical components of the motor. We have an external power supply, so I guess that's really not part of the motor. But we also have a resistor, Ra, and that represents the resistance of the wire that's in an armature winding. And because we have this winding of wire in the armature, we've created an inductor. And so we might as well give that an inductance La. And finally, we have the back EMF. And that's a real interesting behavior that as the motor spins, it actually generates a voltage that sort of detracts from that voltage that's being applied to it. This is the same effect that you get if you were to use a motor as a generator, attach a wind turbine to it and spin it. So now let's use KVL. So we have some sort of current flowing through this circuit, and we have a bunch of voltage drops across it. And then we just start writing out KVL. So we have a voltage rise here, a voltage drop across the resistor, and then we have another voltage drop across this inductor that looks like LA DIA dt. And then finally a voltage drop associated with the back EMF. And there we have it. Now, when you're doing motor analysis, you don't really have to redo the circuit every time. It might not be a bad idea, but you're going to get this electrical equation every single time. Then I like to rearrange the terms a little bit so that we have something that looks like a differential equation in the dependent variable Ia. Now notice this equation is sort of interesting in the sense that I've already replaced E with Ke theta m dot, one of those motor equations. And what it shows is that we have a coupling between this Ia equation, this dia dt equation, and the spin rate of the motor, and of course the input voltage V. Now since there's a gearbox, we also know that theta m is equal to n times theta g. So I can replace that theta m dot with an n theta g. And there we go. Now one more thing, if that LA DIA dt term can be neglected, then this just becomes an algebraic equation in theta g dot. Now the conditions under which LA DIA dt can be neglected are a little bit subtle. It's easy to say, well, if LA is very, very small, then maybe you could neglect that term. But really it comes down to how interested you are in the dynamics associated with that term. And what I mean by that is that this Ia differential equation can have some extremely fast dynamics. And if you're not interested in those and you want to neglect them, then the way to do it is to just remove that LA DIA dt term. Here's a free body diagram, and we're going to be doing this on the output side of the gearbox. So here's our theta g as the dependent variable, the spin of the motor. We're going to say that that direction is positive. And so immediately I can put on this the inertial moment in the opposite direction. And it's the effective inertia times theta g double dot. Now let's also put on here the torque that is transmitted from the motor, that torque that's being applied to the armature inside the motor, going all the way through the gearbox to the output side of the gearbox. So here we have N eta tau m, where again eta is the efficiency of the gearbox. And then we also have some possible viscous damping associated with things that are going on inside that armature area and the brushes and bearings and so forth of the motor. And because it's a theta m dot sort of an effect on the armature, it presents itself on the gearbox side as an n squared theta g dot. Now I can't stress enough this term right here and its importance and its meaning. I've shown it here as an applied torque to this free body diagram, but where it's coming from is that torque that's applied to the armature and going all the way through the gearbox and ending up on as a torque being applied to that shaft of the gearbox. So it's not as if it's an external torque being applied to the output shaft of the gearbox. It's coming from the motor from the other side. So now let's use our Newton's second law sort of a thing for rotating systems. And I'm just picking off the inertial moment first, then the viscous damping associated with the rotating bits of the motor, and then finally the torque due to the armature. And we get that, and we can jiggle that around a little bit. And we have this nice looking second order differential equation in theta g. And notice the coupling right here between this equation and the motor equation, our LA dia dt. And again, the effective inertia is the n squared jm plus jg. Now I've tacked on this other little red term here, the j, that's just saying that if you had another inertial element attached rigidly to the output shaft of the gearbox, then you could tag it on here, just adds to the jg, and you have a slightly different effective inertia. So let's summarize what we have so far. We have this electrical equation. It's just a repeat of what we had on the previous page. Or if you neglect the LA dia dt term, maybe because you just don't want those fast dynamics mucking around with what you're doing, then you get this equation, where the only term that looks like a derivative is this Ken theta g dot. But we'll see in a second that that is almost like an algebraic quantity. Then we have the mechanical equation. And there it is, same as we had on the previous page. And a couple notes. This is a third order dynamic system. As long as you don't neglect that LA dia dt term, you have two states associated with the mechanical equation and one state associated with the electrical. And these two equations are coupled via the IA and the theta g. And finally, if you do neglect that LA dia dt term, then you go down to a second order differential equation, and it looks like this. Now here we can see some of the effect of the back EMF. It presents itself as a damping term. So that's really important just to get a physical sense of what the back EMF does to the mechanical side of the dynamic system. Now here's another thing we can do if we have neglected that LA dia dt term. I'm just going to take this equation and say, well, you know what? Instead of theta g dot and theta g double dot, I'm just going to replace those with omega g and omega g dot. So writing that equation in terms of speed. And we get this. And now if you look at that, you'll see that it's a first order differential equation in omega g. And we could write it as a transfer function, and it looks like this. So here's our motor transfer function for the simplified case where we remove the LA dia dt term. And those terms in that transfer function have some very nice physical properties. The K is the DC gain, and the capital T is the time constant. If you're unfamiliar with those terms, there's some other videos that I do that describe exactly what those are. Well, now let's work an equation where we develop the differential equations for a DC motor actuated dynamic system. And here it is. We're going to have a motor and a gearbox attached to a load, this nice orange load, via a shaft that has a little bit of compliance associated with it. Now the starting point for a lot of modeling, especially rotational systems, is to define some sort of motions for the rotating bits. So I have theta L for the load and theta G for the output side of the gearbox. This part is our armature of the motor, and we also have a gearbox. We're going to lump those two things together, of course, and use our effective inertia, etc., that we saw on the previous slide. We also have a compliant shaft and a load. Now let's start looking at the sort of parameters that we might need in doing the model. For the motor gearbox system, we have the effective inertia, the viscous damping that's acting on the armature, that's BM, RA, LA, those circuit parameters, the armature resistance and inductance, the back EMF and torque constants for the motor, you get those off a data sheet, the gear ratio for the gearbox, and its efficiency, eta. Now, by the way, I'm just going to use a very basic efficiency model. There's many more complicated ones that take into account, that might vary the efficiency as a function of the load and things like that. But we'll just use a constant efficiency in this work. For the compliant shaft, we have some stiffness and damping. I'll denote those as K and C. And for the load, we have an inertia, JL, and let's say that we're rubbing that load on some sort of a surface, and so there's a little bit of viscous damping associated with it. We'll call that BL. Well, here's our electrical equation. It really doesn't change anything from what we had before, so we can just write that down. And I should have set that equal to 0. So let me get that in there. There we go. And now we have the mechanical bits of the model. And so we have a gear ratio, theta M is equal to N times theta G. Now just take a moment and think about the physical nature of that. It says that if the output shaft of the gearbox rotates, let's say, once, and the gear ratio is 10, then that little motor had to spin 10 times to make that happen. And we have our old buddy here, the effective inertia. And here's our two motor equations, tau M and the back EMF, just equal to these constants times armature current and the spin rate of the motor armature. Now let's go after some free body diagrams. So we have one for all the rotating parts of the armature and gearbox, so it's kind of like this part. And then we have the free body diagram of the load over here. Now notice I've kind of ignored the shaft, and I suppose I should have mentioned that I'm going to assume that the shaft is massless. It has this pesky compliance, but we're not going to get into the mass of that shafting. All right, so we have theta G in that direction. We can put on the inertial moment. Beautiful. And there is the torque that's transmitted from the motor all the way to the output shaft of the gearbox. There's the viscous damping term that's acting on the armature. And now we can make our way over to the load. So here's our inertial moment for the load. There is the viscous damping that's associated with this load rubbing on something, perhaps. And now we have this interaction torque or moment due to the compliant shaft. Now there's a lot of ways to come up with that. What you can do is postulate some positive rotation of each of these pieces. So some positive rotation of the load and a positive rotation of the output shaft of the gearbox. And then what you do is imagine what sort of torque is created or moment is created and how it affects the two ends that shaft is attached to. So let's do it this way. Let's say that the load has rotated just a very tiny amount, but the motor has rotated quite a bit. So the compliant shaft is twisted up substantially and is now applying a significant torque on the load to spin it in the direction that we've defined as positive. So that means that this moment that is tending to move the load in the positive direction is equal to K theta G, all that twist of the output shaft of the gearbox, minus anything that the load rotates. And of course, we just have an equal and opposite moment on the output shaft of the gearbox, theta G body. Now, once you have that down, it's easy to put in the damping. I mean, you could play the same mental game for speed, but it's just a lot easier in that case to replicate the same form for speed. Now what we're going to do is make a state space model of this where the input is the voltage and the outputs are the speed of the load and the armature current. So before we make the state space model, let's just rewrite the free body diagrams from the previous page, and then we will just tabulate all the moments that are acting on these to generate some differential equations. So starting with the output shaft of the gearbox, we just have the inertial moment, we have the torque that's being transmitted through the gearbox from the armature all the way out to that output shaft of the gearbox, and now we have the viscous damping associated with what's happening inside the gearbox, and then finally the shaft compliance terms. So we have a stiffness and a damping, and we set that equal to 0. And then we do a similar thing for the load. Just adding up all those moments. And of course we have the equal and opposite damping and stiffness associated with the relative rotation between those two bodies. And now let's just rewrite this a little bit. So jiggling some things around a little so that we have a theta G double dot equation and a theta L double dot equation. And now we can throw in our electrical equation. And look at that set of differential equations. This is the model of the dynamic system. It's fifth order, 2 states associated with theta G, 2 states associated with theta L, and a current state. So now let's do the state space. So first we'll just rewrite these differential equations that we had on the previous page. Nothing new here to see. And then we'll define some states and use these equations to fill out our state space system, which looks like this. And if state space is a little foreign to you, then I have some other videos that describe how to do that. But basically we're going to take this set of differential equations and write them as 5 first order differential equations and an output equation. So I'm going to define the states. You know, there's an infinite number of ways to do that really, and here's one. So I'm going to have theta G and theta L as my first 2 states, and then speeds for my next 2 states, and finally that little armature current. Now what you do is just start taking the derivatives of those states and write that in terms of the states. So x1 dot is just equal to theta G dot, which is x3. And x2 dot, you know, if I differentiate that, I get theta L dot, which is x4. The tricky part comes in here, where we go x3 dot is equal to theta G double dot. I no longer can just look at these definitions and pull that out of my hat, so I have to go to the differential equation. And I go right to there. Boom. And I say, okay, theta G double dot, I have to solve that. And you just do it piece by piece. You know, you can imagine every term in there is going to be divided by the effective inertia, so we're going to see that in the denominator of a lot of things. And if I sort of do it in the sense of the states going from x1, x2, x3, the very first one I have is a k theta G, is this one right here. And when I move it to the right hand side of that equation, I get a negative k over J effective times theta G, which is x1. So there's a lot of, you know, algebra going on there. But, you know, eventually, and if you're very careful, you can make it all work. So here's that term. And then I'm pulling out the theta G term. So I've got the n squared bm plus c over jf. We just got to keep track of those signs. That can get kind of tricky sometimes. And here's that term. x4 is theta L dot. And finally, the IA term, which is an x5 Doesn't really look like an x5 there. Let me make that look like an x5. Okay, so that's our x3 dot equation. Now we do the same thing for the x4 equation. And now I have to use that differential equation. So we're going to see JL in the denominator of a whole bunch of terms. So you can go ahead and go through that same process I just kind of walked through in the x3 dot equation and get this. And then finally we have our IA equation. And of course we have to use that one. So there it is in terms of x1 through x5, and now we have to fill out these matrices. Now the way I like to do this is to work with the most complicated equation first, otherwise I run out of room in these A matrices. So I'm working with this equation first because it has the most terms and the most real estate needed for the A matrix. And really I just copy that equation right down to here and then remove the x1, x2, x3, and x4 and x5s, and everything is in the right spot. And voila, we have that row of the A matrix. Now keep in mind that that row gets multiplied by x, so this gets multiplied by x1, that by x2, by x3, etc. to form that equation. So it all works out. Now let's go to the x4 equation. Again, just take this, copy it down here, remove those x1, x2, x3, etc. from the A matrix because it's getting multiplied by x on the right hand side, and you're good. And there's our IA equation. These are very nice. Those first two, I'm just doing those two. Pick up an x3 and an x4. And that is it for our A matrix. Now you can go through that process for the other matrices, and here just copying out the A matrix again. And then here's our B matrix. So that's how the input voltage gets into the differential equation. And there's our C matrix and D matrix. And C and D are for the outputs. And remember, our outputs are the output shaft of the gearbox. Or no, it's the load, I'm sorry. So it's the load speed and the armature current. So there we go. Now what we'll do is go into MATLAB Simulink, and I'm using 2020A here, and in particular I'm going to take this state space system and throw it into a state space block. That's pretty easy to do, but then also model the system using some of the Simscape blocks, and that will give us two versions of the same model, one formed with state space and the other formed using the components from Simscape. And if we're lucky, the response of those two models will be identical. And what do I have in here? So I have a script that sets up all the parameters. Let's just take a look at that. Now that's a big thing, so let me squish it down just a little bit. Maybe, how about, whoops. Hopefully that'll work. Great. So just do a little bit of cleanup, clean out the simulation data inspector that pops up in Simulink, Simscape, etc. And then set some parameters. So here are some numeric values for all the bits of our model. Here's the motor, the armature inertia, the armature inductance, resistance, etc., the torque constants. Notice the numerical values are the same because I've used nice parameters, or units, I should say. Here's our gearbox stuff. Let's use a gear ratio of 10, a little bit of mass moment of inertia in the output side of the gearbox, and here's our load. A little bit of damping. Oh, I'm sorry, this is the shaft damping. It looks like I'm setting the that rubbing that I made such a big stink about equal to 0. So it's in the model, but I'm just setting it equal to 0 here. And I wrote a little function here to fill out the state space matrices, which is really just sitting right here. And just extract out all those little pieces. So for instance, you send it the argument, let's look at that, the motor, gear, and load structures, and I've just labeled those as MG and L, or named those as MG and L here, so that I could more efficiently just pull things out of them. Now the reason for doing that is so that I can write these state equations in the form that they looked like in my notes, and that will help me to not make mistakes. So I can look at these from a quality standpoint, sort of a quality check, say, oh yeah, in my notes I have n squared bm plus c, and I see it just like that. If I had given these some other names, then I have to do a mental mapping between my notes and what I have written in the code. Highly recommend that. Adds just a wee bit more time to the execution of the code, but you'll never notice it. Okay, so let's run that. Boom. So this is just setting up all the parameters in the workspace. So if I go over here to the workspace and do a whos, I can see an A matrix, B, C, D. I've got my little gear structure. I can look at what's inside there, and it's all beautiful. I set some initial conditions. Looks like all zeros. What else do we have here? So for those of you that have done some work in state space, let's just take a look at this A matrix. There's the 5x5 A matrix that we had in the notes, and if we were to look at the eigenvalues of that, that gives us an indication of the characteristic response of the system. This pole right here, which I would call sort of a fast pole compared to everything else, is associated with that armature inductance. So if we had neglected that term, we would have removed some states from this, well, one state actually, and this would have been gone. So if you're not interested in those fast dynamics, then one way to get rid of them is to set the LA DIA DT term to 0. Okay, enough of that. Let's take a look at the model. Whoops, and look at that beautiful thing. So we have a state space system here. If I double click into that, so double click into that, and we have our matrices and the initial conditions. Not too surprising. And I'm demuxing that and then picking off the speed. And voltage is coming in. So let's go back out. The voltage that I'm poking this thing with is a bang coast bang, or pulse coast pulse kind of a thing. We'll look at it in the data inspector in a minute. You can see I'm logging a bunch of things. But that voltage goes into the state space model, but then it also goes into all this. And this is our Simscape model that is just a different way of modeling. So I'm taking that voltage command and then using a power supply block to create a physical voltage that is the input to a motor. And if I double click into this motor block, look at all those cool things. I get to set the armature resistance, inductance, the torque constant, motor inertia, motor damping, viscous damping, etc. So you can see that this is a more sort of low-level way of specifying the parameters. Here's our gearbox. Here's our gear ratio. Wonderful. And this is the inertia on the output side of the gearbox. And this is our load inertia. And in between there is our compliance shaft. A little bit of damping, a little bit of stiffness. Well, let's run it. Okay, it's running. Okay, done. So I go to the data inspector and cross your fingers, please. So let's see what we have here. What we should see is that the speed from the state space model matches up with the component-based model that we made in Simscape. So to do that, we could look at the load. This is from the Simscape model, and here's the speed of that load. It's got some wiggles in it because of that compliant shaft. And now I was also logging the state space model speed right here. So let's overlay that. Is that some sweet action or what? So they line up quite nicely. Let's look at the armature current. So I'm going into the motor of the Simscape model, and there's the armature current. It's really just following the voltage pretty closely with a little bit of a scale factor. So we can look at the voltage here, if I click there. Actually, not much of a scale factor at all. So here's the input voltage, goes up to 20. Here's the coast, another negative 20, back to 0. And if I zoom in just a little bit, we can see that the voltage in green is this step-like thing, but the armature inductance, or the armature current, has a little bit of wiggle to it and just a little bit of, you know, difference in gain, if you will. Okay, so that's great. Now let's just look at one of the advantages of the Simscape model. So imagine that we now want to model a slightly different system where we have yet another load attached to our load that we just dragged a model for, and it's attached to it via another spring and damper system, another flexible shaft. Now if we went back to our free body diagrams, we could certainly do that. We'd redo all of the analysis and, you know, come up with another second order differential equation. Or if I am comfortable with this model, I can just copy that, paste it. Where did it end up? There it is. So paste it, and I'll just attach it right here. Boom. I've now just attached a new inertia, another inertia, to the output of the orange inertia that we had in the other model. So let's go ahead and change this inertia. I'm going to, I don't know, multiply it by 10 or something. And I now have a new model. Brand spanking new model. This is called load 1 over here. So when we look at it in the data inspector, it will be called load 1. Now notice the state space model no longer matches up with our Simscape model, which is totally, you know, fine. Let me get rid of these. And down here, we'll look at the output speed of that new load. And it's thinking, and there it is. So, you know, we had quite a bit of compliance here. So that other load is slowly coming around and, you know, starting to spin a little bit. So the reason for showing that is just that if you have a model that you've sort of verified, in the sense that you've matched up the response of this Simscape model with your state space model, these are pretty easy to extend into other things if you want to. Now from a control design standpoint, which is certainly the bias of a lot of these videos, you definitely want to have some differential equation model of your plant, because you're going to use that for designing your control system. This sort of model really isn't going to help you very much for coming up with what the controller should be for achieving some sort of closed loop response. Great for evaluation and simulation, but not so great for control system design. Okay, again, a rather long video, but hopefully that was of some use. Thanks for watching, and bye-bye.